electronic device we use today, from smartphones and laptops to electric vehicles and artificial intelligence systems, depends upon one important component, and that component is integrated circuit or IC. But have you ever wondered how these tiny chips are designed? A modern processor can contain billions of transistors, and designing such chips requires specialized engineers called as IC design engineers. An IC design engineer designs, tests, and optimizes semiconductor chips that power modern technology. So in this video, we will understand the complete career roadmap step by step to become an IC design engineer, starting from the basics and moving towards advanced industry skills. Also, just a quick information to help you start with your journey, Simplilearn in collaboration with IIIT Bangalore offers the advanced certification in UI/UX design with generative AI. This 5-month live online program is designed to help you master essential UI/UX skills like design thinking, UX research, wireframing, prototyping, usability testing, human-computer interaction, and much more. Here you will get hands-on experience with 25 design tools, including GenAI-powered design tools, and work on portfolio-ready projects covering areas like AR, VR, and XR prototypes. The program also includes mentor-led project support, masterclasses from IIIT Bangalore faculty, and practical assignments to help you build industry-relevant design skills. So, by the end of this program, you will have the skills and portfolio ready to explore roles like UX designer, UI designer, and product designer. So, if you are looking to build your career in UI/UX design and learn how modern designers use AI-powered tools, this program can help you take the next step. So, why wait? The program link is given in the description box below. Go check it out right away and start your design journey today with Simplilearn. So, without any further ado, let's get started with IC Design Engineer Career Roadmap. So, the very first step is understanding the IC design flow. Before learning any tool or programming languages, it is important to understand how a chip is designed. So, the IC design procedure begins with the architecture design, where engineers define the purpose of the chip, its functionality, performance goals, and overall structure. Next comes RTL design, where engineers describe the hardware behavior of the chip using hardware description languages, that is HDLs, like Verilog and System Verilog. After RTL development, engineers perform verification to test whether the design works correctly and identify any issues before manufacturing. The design then moves to synthesis, where RTL code is converted into a gate-level design using logic gates and optimized for performance, power, and area. In the physical design stage, engineers convert the logical design into actual chip layout by placing components and creating connections on the silicon. Before manufacturing, the design undergoes sign-off verification to check timing, power, and manufacturing. Finally, the approved design goes for fabrication, where the chip is manufactured, followed by testing to ensure the final clip works correctly. So the complete flow looks like this: architecture design, then RTL design, then verification, then synthesis, preceded by physical design, fabrication, and finally the testing procedure. See, understanding this complete journey gives you a clear picture of where an IC designer and engineer actually works. Now coming at step 2, build electronics fundamentals. The very first thing in your learning journey is building a strong foundation in electronics. So start with digital electronics. You should understand number systems like binary and hexadecimal, logic gates, Boolean algebra, maps, combinational circuits, and sequential circuits. You should even learn the basic digital components such as multiplexers, adders, encoders, decoders, and registers. These components are the building blocks of every digital chip. For example, when a processor performs calculation, controls memory, or executes instructions, millions of these basic digital circuits work together. A strong digital electronic foundation makes advanced IC design much easier. Now coming at step 3, that is learning semiconductors and CMOS basics. So this is a step where you will understand how chips are physically built. Every IC is made up of using millions and billions of transistors. So you need to learn semiconductor physics like PN junctions, MOSFETs, CMOS technology, power consumption, leakage current, and fabrication process. The most important concept is the MOSFET transistor. A transistor works like a tiny electronic switch. Billions of these switches are combined together to create processors, memory chips, and AI accelerators. Understanding CMOS technology helps you understand how hardware actually works at the silicon level. Now coming at step 4, which includes learning programming skills. Many beginners think IC design is only electronics, but programming skills are equally important. So the first programming language you should learn is C programming. Here you can focus on variables, loops, functions, arrays, and memory concepts. Next, learn Python. Python is widely used for automation, testing, writing scripts, data processing. You should also need Linux skills because most semiconductor design tools run on Linux systems. Here, you should learn basic commands like creating files, managing direct, running scripts, working with terminals. So these skills are used daily by semiconductor engineers. Now the step 5th, learn hardware description languages. The most important technical skills for an IC design engineer is learning a hardware description language. So the two major languages are VLOG and System Verilog. Unlike software programming, where you write instructions that execute step by step, hardware description languages describe actual hardware circuits. For example, instead of saying add these two numbers, you describe create an electronic circuit that performs addition. You can start learning Verilog concepts like modules, inputs and outputs, data types, operators, always blocks, and clock signals. After learning basics, create small projects like multiplexer, counter, ALU, communication module, and even memory controller. These projects help you understand real hardware design. Now coming at step 6, that is choosing your IC design career path. After learning the fundamentals, you need to choose a specialization. So basically, there are mainly 4 career paths in this field. Path 1, that is RTL Design Engineer. RTL engineers design the actual hardware logic of the chips. Their work includes writing Verilog or system Verilog code, designing digital circuits, optimizing performance and power. Important skills includes advanced RTL coding, computer architecture, processor design, low power design. So the career growth looks like this: RTL engineer, then senior RTL engineer, and then associate architect. Now let's look at part 2. You can even go for design verification engineer. Verification engineers ensure that the chip works correctly. They create test environments to find bugs before manufacturing. They learn components like system Verilog, UVM methodologies, assertions, functional coverage. So a good verification engineer prevents expensive chip failures. And the career growth looks like this: verification engineer, then verification lead, and finally verification architect. Now the part 3, physical design engineer. Physical design engineers convert the logical design into an actual chip layout. They work on floor planning, placement, clock redesign, routing, and timing optimization. They use industry tools like Cadence Innovus, Synopsys ICC2. So the career growth in this field looks like this: physical design engineer, then physical design lead, and finally chip implementation architect. Now the last path, that is FPGA engineer. FPGA engineer implement hardware designs on programmable chips. They work on hardware acceleration, embedded systems, and prototyping. FPGA knowledge is also useful for learning ASIC design. So this was a very important step, choosing your career path. Now coming at step 7, that is learning industry tools. After learning concepts, you need exposure to professional tools. So the important categories include simulation tools that are used to test hardware designs. For example, model sim, or next coming to synthesis tools. These converts our code into hardware circuits. For example, Synopsys Design Compiler and Cadence Genesis. Now the physical design tools. These are the tools used for chip layout. For example, Cadence Innovus and Synopsys ICC2. And last but not the least, verification tools. These tools are used for advanced testing. Example, Synopsys VCS and Jasper. See, learning these tools makes you closer to industry requirements. So, learning these tools are very important. Now, coming at step 8, building real projects. Projects are extremely important because semiconductor companies look for practical experiences. So, the beginner level projects includes designing digital clock, traffic light controller, ART controller, and FIFO memory. Now, the intermediate projects includes ISV processor, cache controller, bus protocols like AXI and APBs. Now, coming at advanced projects. You need to complete an end-to-end ASIC flow that look like this. RTL design, then simulation, then synthesis, then physical design. You can also practice using open source tools and hardware platforms. Now, coming at step 9, prepare IC design interviews. For interviews, you need to focus on 4 major areas. First, digital electronics. Here, prepare for flip-flops, FSM, timing concepts, and logic design. Next, Verilog and system Verilog. Here, prepare for RTL coding styles and design problems. Now coming at the third major area, which is computer architecture. Here, learn for CPU pipelines, cache memory, and processor design. Last but not the least, semiconductor basics. Here, understand for CMOS inverters, MOSFET operation, power consumption, and fabrication process. So, these were the 4 major areas you need to focus for your interviews. Now, let's look at the complete IC design engineer career roadmap in a nutshell. So, first start with digital electronics. Then, move towards semiconductor fundamentals. Third step, learn the programming languages. Then, learn hardware description languages. At step 5, choose your specialization. Then, learn EDA tools. Then, build hardware projects. And finally, prepare for interviews. This is how you can become an IC design engineer. So, with consistent learning and hands-on practice, a beginner can become industry-ready within 12 to 18 months. IC design is a challenging field, but it plays a critical role in the future of technologies like artificial intelligence, automation vehicles, and advanced computing. So, if you're interested in hardware, electronics, and creating a technology behind modern devices, then IC design engineering can be an excellent career path for you. So, if you found this video helpful, then do like the video, share it with your friends, and subscribe to the channel for more such content. Thanks for watching, and I'll see you in the next one.